All right. Good morning, everybody. This is day 2 of the OpenMP News Conference, and guess what? They're here. We have the lanyards, we have the shirts. So finally, UPS they did their job. All right. So it's my pleasure to introduce Meifeng. She's working as a computational scientist at Brookhaven National Laboratory. She's interested in high-performance computing, computational science, quantum physics, chromodynamics, and she's going to give us a presentation about how to apply OpenMP to quantum chromodynamics, what is missing, and what is working today. So, take it away.
Thank you, Michael, for your introduction. Yeah, so as our chairman mentioned, from Brookhaven National Lab, and my background is in lattice quantum chromodynamics in high energy physics, and but in the last few years I have been focusing on high performance computing in general, so outside of lattice QCD itself. And first I would like to thank the organizers for giving me the opportunity to speak here, and I also want to thank you in advance for coming here so early in the morning. So here's the outline of my talk. Is there a pointer? That's okay. So, I know the audience have very diverse backgrounds. So I just want to give a very quick introduction, very high-level introduction to what lattice QCD is and what it does, and especially in terms of the software and programming model requirement. Thank you very much. What we are trying to achieve. And just to provide some historical perspective, I'll actually go over some lattice QCD specific hardware and the evolution of the programming models associated with the hardware. And so in particular, lattice QCD community have been engaged not only in high performance computing on in the simulation and software side, but also in the hardware design. So I'll mention a few of the special purpose supercomputers for lattice QCD. And of course, lately the commodity hardware based on CPUs and GPUs are commonplace, and we are also switching to using these more common hardwares as well. And of course, the main focus of this workshop is OpenMP, and for the OpenMP the development of software using OpenMP. So I'll also talk about the lattice QCD software. And the third part of my talk will be focused on some projects that I have been personally involved in. First is some optimizations that we do to a specific compute kernels for lattice QCD. And I'll focus on the OpenMP related part. And then the second project is part of the QCD exascale application development project, which is to investigate different performance portability programming strategies for lattice QCD. So lattice QCD stands for lattice quantum chromodynamics, and it is a numerical framework to simulate the subatomic particles called quarks and gluons on the supercomputers, starting with the fundamental theory of strong interactions. And the basic numerical techniques are very simple. You basically discretize the theory and put them into, so you can visualize now the space-time as a discrete lattice, and all the physics happening on either the lattice sites or the links connecting them. And we do multi-color simulations from the theory, and to generate the quantum fields of interest, and then we can do some physics measurements on top of them. And the physics results we obtain can be compared to experiments or can help us make theoretical predictions. And the pictures on the right are just some visualization of what you may get from the multicolor simulations, or what the space-time will look like, the different densities of the topological charge. I didn't change this slide to remove the equations, but this is what the compute kernel of lattice QCD is like. It's basically a matrix vector multiplication. This is what we call the D/ operator. So D is a very high dimension matrix, and phi are the vectors. And if you this is basically just stencil operator, but in 4 dimensions. So it's a 9-point stencil operator. And this operation makes up, depending on the type of calculations, it is the most computationally intensive part of lattice QCD simulations. So sometimes it can take up to like 90 or 95% of the computation time. And the algorithm motives behind lattice QCD, as I mentioned, we do Monte Carlo simulations. And then we also need to use molecular dynamics to evolve the gauge field complications to move through the Monte Carlo chain. And we also need to solve these linear systems of equations. And sometimes we also need to use eigenvalue solvers. And these are just some kind of the graphs that we want to evaluate from these simulations. And the goal of lattice QCD simulation since the very beginning is to understand the fundamental symmetries in the universe and help us understand the properties of the fundamental particles. And with the increasing computing power, especially towards the exascale era, our goal is to improve the precision by an order of magnitude and also extend the type of calculations that we can do on the supercomputers to resemble more the reality. And from the software point of view, we are designing a new software framework for the exascale computing, and some of the requirements of this new software include efficiency. So we want to be able to make the best use of the new exascale architectures. And especially for us, communication has always been the bottleneck to be able to strong scale to many compute nodes. And we would also like to have flexibility in the software that we have so that the not so programming savvy users can implement different algorithms and perform different physical calculations without having to go through the low level hardware specific implementations. And both for the maintenance and for the development of the software, we also want to try to achieve performance portability in the design of the software. So I will talk about what the current software we have right now, and you'll see why this is very important for us. But I think this is a common challenge for all the application developments right now. So lattice QCD requires a lot of computing power. Just to give you an idea, a lot of the calculations we are doing right now, we have done so far, require computing on like several racks on the Brookhaven Q supercomputers for months or even years to get certain precision. And needless to say, the precision we can achieve so far is not high enough. Otherwise, we would just stop working. So it's a very computation intensive calculation. And luckily for us, the uniform space-time structure of the calculation makes it very good for parallel computing. So here is just a sketch of how we parallelize our calculations. So this is in the 2-dimensional space-time, of course, and for the dots they are the lattice sites in our simulations, and the squares are the compute nodes. And we basically just divide evenly the lattice to map onto the different compute nodes. And because the data we need are basically nearest neighbor data, so what you need to do is you need to send the data at the boundary to the nearest neighboring nodes. so that when you do the simulations, you can communicate with the whole system. So this is the traditional way of mapping the lattice to the compute nodes, and later in the new software that we are developing, this mapping may change a little bit. So back in the 90s, because the PC clusters were not so common then, lattice QCD series actually designed their own supercomputers, and this is the one that I actually used when I started as a graduate student at Columbia, which is the QCD SP machine. It stands for Quantum Chromodynamics on Digital Signal Processors, and it is based on the signal processors by, I think, Texas Instruments. And it's very nice because it has the 4D mesh for communications. It has the built-in hardware for the type of communications that lattice QCD simulations require. And it was so it had very good price performance, and so it won the special price performance prize, Golden Bell Prize in 1998. The machine was capable of running multiple instructions or different instructions on different nodes, but typically it was programmed in the single program multiple data paradigm. And because there are no shared memory, so there's no OpenMP threading used on this machine. And also it has some hardware specific, its own message passing protocols. So we also didn't need to use MPI, so quite different from what we are used to nowadays. And the next generation of the lattice QCD machine is called QCD-OC, QCD on a chip. This machine was based on the PowerPC processors, and it was also designed by the lattice series. It was a collaboration between Columbia, Riken, Brookhaven Research Center, BNL, Edinburgh, and also IBM. And similar to QCD SP, it also has this built-in high-dimensional mesh for communications. And as is true for all the hardware architecture evolution, now the price performance it's like an order of magnitude better than QCD SP. Here, still no shared memory, so no threading. The internal communication now can be done through either MPI or just our own QCD message passing QMP. So QMP is a high-level layer that was written on top of either MPI or the hardware-specific communication protocols. And this is just a picture of QCD-OC at BNL and some of the people who were involved in the design and installation of this supercomputer. And so lately, in the last 5 to 7 years, we have been using the QCD with chiral clocks, and this was a prototype machine for IBM's Brookhaven supercomputer. And now you can see here's a comparison between QCD-OC and QCD-CQ. So on the node level, QCD-OC only has one compute core. That's why we didn't need to use threading. But QCD-CQ, each node has 16 cores, and they share memory. So it became important to use threading, either OpenMP or other threading programming models. And this machine has been in use since 5 or 6 years ago, and we are currently still using the Brookhaven supercomputer either at BNL or the one at Argonne. So the reason I wanted to show you this hardware evolution was to show this is tightly related to the software we're using, because lattice QCD software has been evolving with the hardware. So as we try to make best use of the available hardware, we also need to make changes to the software stack to be able to support the new architectures. So now it's very common to run simulations on PC clusters interconnected with high bandwidth fabrics. However, I just noticed that 15 years ago, this paper about lattice QCD on PCs had a title with a question mark. And because it wasn't very well known that you could actually perform lattice QCD simulations on just regular personal computer processors. And it was very different 15 years ago, but now a lot of the, I'd say most of the PC clusters have processors that contain multiple cores, and they share big CPU memories. So it became important to use shared memory programming models such as OpenMP to get good performance on this type of hardware. But I wanted to mention that back maybe 10 years ago, OpenMP wasn't very commonly used for lattice QCD simulations. What we often did was to run multiple MPI processes per node. When you have 2 or 4 cores, it wasn't so bad if you had to run multiple MPI processes per node. And also because it was easy, because we already had the code that could run, that had MPI implemented in it. Nowadays, the landscape has changed a lot. So especially with the new many integrated core architecture, when you have 60 or 70 cores per node, running many MPI processes per node becomes very inefficient. It's also not a very sensible thing to do. So nowadays it becomes very important for us to use OpenMP threading in the code. And here are just some pictures of the different dedicated lattice QCD clusters in the US. This was the 10Q cluster at JLab, and this is the JSAC cluster at Fermilab. And the 10Q cluster at JLab has been replaced by a nice blending cluster, also for lattice QCD simulations. And now GPU computing also becomes very, very well known and common. And lattice QCD theorists started to explore the possibility of using these GPUs to do QCD simulations, again back to about 10 years ago. And in this paper, the authors, they actually used OpenCL to program the GPUs. And then all these GPU programming models have been explored by the lattice QCD community, OpenCL, OpenACC, and CUDA. And the most popular program model used right now is, of course, CUDA, thanks to the CUDA library that was developed first by the group at Boston University. I'll talk a little bit about it when I talk about the software for lattice QCD. So as you can see, with the different hardware architectures evolving over the years, lattice QCD software has to be adapted to use these new hardware architectures in the last 20 years. And as a result, there are a lot of different modules that were written to maximize the performance on these different hardware architectures. And this is a diagram showing you the software landscape in the US. This was the software developed under the DOE SciDi program. And there are basically 4 levels of different code bases. The level 1 just supports just basic linear algebra, multi-threading support, message passing support. And the level 2 is more lattice QCD specific, QDP++, QDP, so QDP and QDP++, they both support lattice data parallel layer, and QIO supports the I/O of the lattice QCD simulations. And the level 3 involves codes that are related to the algorithms that we use, such as the linear solvers, or called the inverters, and different discretizations, different matrix vector multiplication routines, and some other C-based optimizations. And CUDA here is what I just mentioned. CUDA is a QCD library written specifically for GPUs, and it's written in CUDA, and it has been under active development even now. So it has also been evolving to catch up with the evolution of the GPU architectures themselves. And then the top layer is the application layer. These codes are the what physicists use to do the physics calculations. And Chroma was developed and maintained at the Jefferson Lab, and CPS stands for Columbia Physics System, so it was developed mainly by the physicists at Columbia University and Brookhaven National Lab. This is the one that I have been using myself. And FEO is a new application suite based on Lua, and it calls the underlying low-level routines for lattice QCD. Milk is another US-based lattice QCD software, and QRUA is also based on Lua, but it has the different functionalities from FEO. So this is what the current US QCD software is like. And the hardware-specific implementations are usually buried in this level, like inverters or the D// operators, or CUDA. So CUDA has inverters and all these performance-critical parts of the lattice QCD simulations. And as I mentioned many times, because the lattice QCD software has evolved over time with the changes of the hardware, the program models used a mixture of many things. And over the years, MPI plus X has become the most popular choice. So that's why we are planning to develop a new software stack that can basically achieve performance portability, so we don't have to maintain so many different code bases for different types of architectures. And for the absolute performance critical part, we may still think about calling some of the low-level optimized libraries, domain-specific libraries like CUDA or other, or the libraries optimized for other architectures. But we are hoping that we could have a unified layer for the other part of the lattice QCD software. Okay, so I haven't talked much about OpenMP yet. But I hope that gave you an idea of what lattice QCD community, where lattice QCD community stands in terms of the usage of OpenMP. What I'm going to talk about next will have some more technical details related to OpenMP. The first one is a project that I did in the last 2 years with with a small company in New York Reservoir Labs to optimize the D// operator in Columbia Physics System. So you don't have to read the equations, but what I want to point out is that this is the operator that we try to optimize, and it is the generalization of the D// operator that I showed at the very beginning into 5 dimensions. And what's nice about this operator is that one of the pieces, this piece, is completely independent of one of the dimensions. So which means it's very good for vectorization. So the optimization we did was first on the single node, and then we try to optimize the MPI scaling as well. So this is just a slide showing you the vectorization that we had to do. You are all familiar with the SIMD optimization, I'm sure. So if you want to program SIMD machines, data layout is the key. You need to make sure that the data layout for your simulations can allow you to do vectorization, for the type of operations. And as I mentioned, in this operator, there's a one dimension or one index that is completely independent for different sites. And this is just the layout that we use. So we use red-black checkerboarding, so it only has half of the length of the fifth dimension. And so this is what the data layout looks like. The optimization we did was for Haswell architecture, so AVX. And we had to use SIMD intrinsics to implement vectorization for this operator. We tried just putting in Pragma OMP SIMD, but the performance was very poor. So this is one of the areas that I'm hoping OpenMP and the compiler community could help improve, so that we don't have to go down to the intrinsics to get good performance. I'm sorry?
So you vectorize over NS, right?
Yeah.
What's the size of that?
Oh, NS. So NS is usually on the order of 10. So vectorizing over the S direction has the disadvantage that NS has to be multiples of 16 or 8, or it has to be multiples of the SIMD length of the machine that you are targeting. Yeah. For this particular machine, the vectorization in the S direction allowed us to use NS to be 8 or 16, depending on whether you want to do double or single precision calculations. So these are just some other technical details not related to OpenMP pragmas, or as far as I know, but maybe OpenMP can also help. We tried different things to improve the data locality, for example, tiling, but it didn't help much. And we also tried to use space filling curves. It didn't help much either, but prefetching did help. So this is basically a stencil operator, right? So if we prefetch data needed for the next stencil, we could get about 10% performance improvement.
I'm sorry, I have a question. So you said that OpenMP SIMD didn't work. Now you're saying that if you just turn on QCD option with no intrinsics, you get the same performance?
Oh, this is just the fuse multiply S part. Yeah. Yes, not the just the other arithmetic operations.
I still don't understand. Are you writing intrinsics or not?
No, not for the FMA intrinsics. We didn't use FMA intrinsics, but we used the intrinsics to load and store data and.
Okay.
Yeah, so for the computation part, lattice QCD is very simple in the sense that we basically just have nested loops. So the most commonly used OpenMP pragma is parallel for, and depending on what the operations here is, you may use collapse. But for this particular case, we couldn't use the collapse course because of some dependencies. So we tried three different strategies to use the OpenMP pragma. First is just to parallelize the outermost loop. In this case, it's the T loop. And we also manually expand the loops into one single giant single loop and use OpenMP parallel for the loop. And the other approach is to use the same linearized loops, but we use explicit work distribution to basically tell the threads which part of the array matrices that you are supposed to work on. So if the compiler does a decent job, then these two should basically be equivalent. So this is just some benchmark results for different lattice sizes or just different workloads. And you can see for one thread, the performance for these different implementations are basically identical, as you should expect. When you increase the number of threads for the simple pragma, because we only parallelize one of the dimensions, so the length is 8. You see that you can't really get scale past 8 threads, so the performance basically just levels off. And for the other two approaches, you see that the performance are basically similar to each other. And for larger lattice sizes, again, you can see the scaling. It actually scales pretty well with the number of threads. And with the larger T dimension here, this is 32, all these implementations basically give you similar performance. Yeah, this is some more checks that we did for different lattice sizes. And one interesting thing to note is that the performance does not really deteriorate with much larger lattice size, even when the lattice didn't fit in the cache anymore, which is a possible indication of poor cache reuse. So this is a room for further optimization. But this, I'm not sure if this is something OpenMP can help or not. We also found that thread affinity was very important to get the good performance. And we use the GCC compiler, and when we set this proc bind to be true, we got much better performance than without it. Yeah, this is, and for the strong scaling, we did overlap computation and communication to basically overcome the communication bottleneck. As I said, the data we need is just the data or at the boundary of the local lattice. So we could do the bulk computation, the stencil computations in the bulk of the lattice while waiting for the data, the boundary data to be transferred. And this is what we did. And in terms of the OpenMP specific part of this implementation, we actually dedicated one thread, the master thread, to be in charge of the communications and the communications only. And the rest of the threads are devoted to the computations. And you may notice that you can probably in principle do this with OpenMP tasking. This is something that we have been thinking about but haven't implemented. But I noticed that some other lattice groups have tried this already. Yeah, so this is some plot showing you the scaling. So this is the ideal scaling, and this is what we achieve. Again, when we go to larger number of nodes, the communication just becomes a big bottleneck. You can see the computation time decreases nicely with the number of nodes, but then the communication time just doesn't decrease as fast. This is why we can't achieve a very good strong scaling for this particular case and for this particular type of architecture that we have tested on.
But you don't really want a strong scale anyway. You want to solve the biggest problem you can, right?
That's right, but well, there are two aspects. So first, we want to solve a very big problem, but we also want to solve the problem as fast as we can. As I said earlier, typical lattice QCD calculation takes months or years to finish. So if we can have very good strong scaling, then you can just reduce the amount of time that it takes to do this particular size. But you're also right. We also want to do as big a calculation as possible. But this, for one particular lattice size, it already takes a long time, so it helps us to have very good strong scaling. So for the remaining part of the talk, I'll talk about something still ongoing for the exascale project. You probably are all aware of the importance of performance portability, and from the current software stack I show you, you understand why we want to attack this problem. A single version of the code is certainly easier to maintain, and we are hoping that we will spend less time on integrating just different levels of APIs with the application there. And the question is, how much performance are we willing to lose in exchange for portability? Because lattice QCD theories developers have traditionally been very good at squeezing the last bit of the hardware performance. And if the answer may be no, but with potentially more diverse architectures, are we able to continue our current approach with just different hardware-specific optimizations for different architectures? It's certainly, the software we have so far is the result of 20 years of development. So it's certainly very, it's very expensive to continue this approach. And the various tools that we have considered for performance portability are listed here. First of all, you're all familiar with the compiler directives such as OpenMP and OpenACC. We were considering OpenACC because we wanted to be able to run on the GPUs as well. And then there are other high-level programming abstractions such as Raja, Cocos, possibly SQL, C++, these are more platform dependent. And we have also looked at code generators or source-to-source compilers such as just-in-time compilation. And recently, my colleagues at Argonne also looking at using this new language called NAME. It's basically a code generator. It generates C code to see if it can be used to achieve performance portability for lattice QCD. I keep mentioning this, but should we design our new software with portability in mind first, and then optimize for performance later, or the other way around? I don't really know. Can we also design our software with performance portability in mind from the beginning? But you've got to start somewhere. So do you want to have portability first and then try to optimize for performance later, or do you want to just write performance code and hope that it can be ported to other architectures easily? And the code base that we have used for this particular project is Grid. Some of you may have heard of it. Grid is C++ lattice QCD library, still being developed by a group at University of Edinburgh, and in particular Peter Boyle. And it was originally developed and optimized for various CPUs, including the Intel Xenon Phi architectures. And now it is being used as a test bed for the QCD exascale performance portability studies. it uses a lot of the C++ 11 features for abstractions and for high-level programming flexibilities. And one nice thing about GRID is that its data layout was designed to match the CPU SIMD lanes. Earlier I mentioned that we simply decompose the lattice, the whole lattice to map onto different compute nodes. With a longer SIMD length, I also talked about the vectorization for the domain wall D/slash earlier as one of the projects. But if I just vectorize over one dimension, I run into the constraint that the length of that dimension has to be multiples of the SIMD length. And in GRID, the lattice, each lattice on a compute node is further decomposed into several virtual nodes, and these virtual nodes are mapped into different SIMD lanes. This approach has the advantage of being able to map onto different SIMD lanes without running into the constraint of the lattice dimensions. And this is just a code snippet showing you what a GRID looks like this is the intermediate level. So there are some architecture-specific implementations for the vectorization. It uses intrinsics, depending on the target. There is also generic implementation without intrinsics. So here you can use OpenMP SIMD. And the data types are highly abstracted. So on the higher level, you won't be able to see all those hardware-specific implementations. And again, we have a lot of for loops. So in GRID, everything is done through a giant for loop, so linearized through the different lattice dimensions. And the most commonly used pragma is, again, parallel for and perhaps sometimes collapse. And with the abstractions done in GRID, you can write very high-level code such as this. So this expression does lattice-wide, a giant lattice-wide matrix multiplications. And here's just some performance on the CPU-based architectures. And you can see the performance is pretty impressive across the board. But it doesn't support GPUs. GPU is not among the supported architectures at the moment. And we started the GPU porting effort about a year ago. And first we tried to use OpenACC, but it was completely impossible with the whole GRID library because of the big copy issues. The data structure in GRID are very nested. And there are also other compiler-related issues. And so last summer, Peter actually just stripped down the GRID expression template into a very small self-contained code to see if we could get this piece of the code to work on both CPUs and GPUs. And the code is very simple. So basically, the key kernel is just this for loop that does that evaluates different expressions. And the approaches we studied include OpenACC. We also tried OpenMP, but it didn't work, and I'll tell you why in a bit. And we also explore just-in-time compilation and CUDA. Of course, CUDA is specific to NVIDIA GPUs, as far as I know, or as of now. And but it is a very mature programming model for NVIDIA GPUs, and it also has pretty good C++ support. But the disadvantage is that you need to write some CUDA kernels, and it is unavoidable to have some code branching, which is not something that we are very fond of. And for the offloading compiler support. Here is some probably slightly out of date list. This was a slide from last year, and you can see in principle OpenMP and OpenACC, OpenMP and or OpenACC should be able to support GPU offloading. But for our specific application, because of the C++ features, using directives has been quite difficult for us. So this is just some potential implementations with different programming models. For OpenACC, it's similar to OpenMP. You see you have this parallel loop clauses and then some data clauses. And OpenMP, you also have data clauses and parallel computing clauses. And then this is just the CUDA kernel that we would need to write if we want to use CUDA as our programming model. And this is some header library that was developed in NVIDIA. And if you use the just-in-time compilation, in principle, you could write it this way. So OpenACC did work for us, but we need to use the unified virtual memory support in the PGI compiler, because we couldn't do manual data copying due to the nested structures, data structures in this code. And OpenMP, we would like to be able to do this, but it didn't work because the compiler doesn't support unified virtual memory. And for these other two, it's just it's fairly simple because it's basically what they can do, they are supposed to do. So I want to point out that even with CUDA, it makes our life much simpler by using the managed memory. So we basically have a custom memory allocator which uses intrinsics on the CPUs, but on GPUs it's just CUDA malloc managed to simplify the data management. So here's just some performance numbers for CUDA, GTFi, and OpenACC. You can see this is just a pure out-of-the-box performance, and you can see OpenACC actually gave us pretty good performance. It's better than the other two models. But because we have more control with either CUDA or GTFi, we could further improve the performance to this. So about 80% of the theoretical peak. This is a GTX 1080, and this is just a streaming test of A times B, similar to the stream triad streaming test. And you can see for these other two models, we could get pretty good performance. The catch is that we had to use coalesce pointer to ensure data coalescing on the GPUs, and we couldn't do that with OpenACC because the code didn't work. So there was some of the challenges that we had. I see that our chairman standing there, so I'll wrap up very quickly. But Grid's data layout can actually be mapped to GPUs fairly easily to get very good performance. So I'm going to skip the details, but I want to show you the performance that we could achieve. These results are the results from the CUDA implementation because of the difficulties with either OpenMP or OpenACC. So this is the result from CUDA for the GPU. So the GPU performances are this one. This is for Tesla. Oh, this is Volta, and this is Pascal. And this is the result for Knights Landing and Xenon. That's Broadwell. This is Intel Broadwell. And you can see the dashed lines are the stream trial results. So for the mini code that we have that is built on top of Grid, we could actually achieve pretty good performance compared to the stream trial code. So we are basically getting the best performance we could possibly expect, which gives us hope that maybe it is possible to write performance portable code. So I want to point out that these results are all obtained with the same code, which is compiled for different targets. I want to skip this one. Yep.
Could you clarify, you said that the memory bandwidth you saturated, so you could not gain more performance, right?
Yeah, so I didn't mention this, but QCD calculations are memory bandwidth bound. So our compute intensity is fairly low. So it's about around 1. Yeah. So let me just summarize. Lattice QCD's regular grid structure is great for parallelization. This is very good for us. And the diverse hardware architectures that Lattice QCD software has been optimized for result in significant division of code bases. And OpenMP is becoming more and more important for us with the increasing the parallelism on the node. And perhaps OpenMP can finally give us a way to achieve this grand unification of the code bases. So we haven't used a lot of the different OpenMP features, but what works quite well for us is the simple parallel for loops, parallel for construct, and sometimes we use the API calls to get more flexibility in the way we want to do the calculations. What may work for us, the SIMD construct can potentially simplify the programming for the vector architectures greatly, and even though it didn't work for our particular case, some recent work has shown that if you have a good data layout, it's possible to achieve very good performance with this Pragma CMD construct, and we may be able to use tasking to overlap communication and computation. And what we really need right now for the C++ applications is the better support for C++ GPU offloading, because the complex C++ programming styles would require the support for decopy or unified virtual memory for the accelerators. And that's all. Thank you very much.
So we do have time for a couple of questions.
Hi, I believe a few slides ago you were comparing the GPU performance of the kernel in CUDA or OpenMP.
Yep. Yep.
I was just wondering, it seems to be that it is a very simple kernel, but maybe hope that the compiler could handle that. I was just wondering, is this just with one particular compiler, or do you also try like CGI or Cray?
So this, for the directive, this is implemented using OpenACC. We only try PGI because we need the unified memory support. And as far as I know, PGI is the only compiler that can support that because of the nested C++ data structures. We really need that support.
So
Yeah.
that X times Y is a really complicated X times Y?
Yes, so this X and Y are arrays of 3x3 matrices. Yeah, so it's a very big, you can just think of them as very big arrays. Yeah.
One more question? Very well. Very close. All right. Thank you.